Let's move on. I invite here Anna Kalyuzhnaya, the head of educational program Digital Technologies 2021 of ITMO University. We all understand that the artificial intelligence term, the second word is prevailing, and Anna will tell us more about it, whether AI is thinking about evolution. Hello, dear colleague. My name is Anna Kalyuzhnaya, and my presentation is called Whether AI Dreams About Evolution. Quite rhetorical question. The mankind dreams that AI should evaluate and come to the state which is equal to the human intellect or become even superior. Although the IBM Vice President, Mr. Watson, mentioned that the requests of the society are quite different. People are afraid of strong intelligence, but nevertheless they'd like to have artificial intelligence to make them better, make them more smart, and be able to generate non-trivial solutions at a regular basis other than it happens currently. As a result, to have a perfect decision-making support system which could give a set of solutions upon request, each of which would bring you to the goal, but have some certain details. And from the point of view of algorithm requirements, it can be implemented if algorithms can efficiently seek for solutions at larger spaces. But do it straightforward is quite complicated and not efficient. That's why we can offer a few ways how to make it in a more flexible way. For example, it is possible to examine the whole space not at once, but incrementally expanding the borders for one object and for the target objective, or to replace the space by the model, or change the way of seeking for this model. All those requirements fit in the open evolution concept, which is another view on the development of self-depending and creative AI algorithms for different engineering tasks. Examples of these tasks, starting from classical designing of classical objects, could be tasks for automated design of chemical substances, biological substances, and automated design of different kind of models. What should be the processes of algorithm to solve such tasks? First of all, they should work very well in high open spaces with super big sizes. So these tools should know how to explore them gradually, to develop their own by changing their own structure, to change the search, and to be flexible enough to be able to solve tasks with big limitations. And these systems should be able to work with continuous and combinatory tasks. Evaluation algorithms allow to do it all and be in line with those criteria. If we set a task to develop a more or less universal algorithmic search engine, the objects should be also optimized. And if we consider different engineering tasks, it turns out that some of them can be formalized in terms of annotation of graphs, which is convenient for different structure when we can explain them in a form of grid or linear 2D or 3D objects, which is also suitable for any other models, either by symbols or in any numerical notation. It is very well translated to computation graphs. These graph structures in a unified form can be put upon the chromosome structure, where the part of chromosome is given for property description of the nodes, which can be more or less complicated. And the second part is given to describe the topology of the whole graph, which can be logged based on the fact whether it's directed or non-directed, and if there are any additional constraints for the structure or no. When we have a uniform notation for graph structures, we can work with them using graph evaluation operators, crossovers, and mutations. The most interesting is mutation, because they allow to delete some nodes, which is the simplification procedure or regularization of the whole structure, and also add those nodes which can be taken from the whole theoretically possible multitude of different nodes of solutions, and in this way we can gradually expand the search area. If the evaluation algorithms so mature, they would capture the world long ago, but they have quite serious limitations and drawbacks. First of all, this is a very long convergence of those algorithms. Secondly, they still cannot guarantee the search of the global optima and the dimensional sparse spaces, and they can get stuck in some local optimums. And finally, some researchers blame them in randomness of operators. So in the high-dimensional spaces, they are oriented blindly. What can we do about it? In order to improve the situation, it is possible to design different hybrid or model solutions or surrogate solutions, where evaluation algorithm can be combined with other procedures or algorithms, for example, regularization, which allow to speed up the convergence, or surrogate solutions which can allow to combine evolution algorithms with different models of algorithms, which allow for the basic algorithm to become smarter. If we build up a model for time rows, we can use localization as a surrogate solution in a Fourier transcription, which allows to find this solution in the synergetic peaks by speeding up convergence and by improving the quality of the solution. Let's consider a few examples. One of the most indicative examples where we can see the application of those ideas in creative design are the tasks of generative design. Generative design is a system of augmented intelligence which allows specialists, subject matter experts, to get populations of optimum or quasi-optimal solutions. In essence, it is an algorithm of intellectual optimization to check validity of solutions or to compute target characteristics. For tasks of developing different structures, normally these models are brought to models of Kugel deformations, which allow to evaluate strength characteristics. But if the task is to evaluate not only the environmental impact, but also the object impact to the environment, we will need additional models. For example, when we have a task to create a system of wave protection for bays and sea structures, we need the model of waves, which would allow us to see how the facility could properly protect the sea zone, the sea region. It can be checked also by physical experiment, by physical models, like shown here as an experiment in the trial basin with microwaves. And a very similar task, but different in size, is the task to optimize microfluid chips to filtrate blood, so-called blood vessels on chip, where the main task is to create optimum bloodstream which would pass through the filter trap and to provide optimal blood flow. It is necessary to place hurdles with the complicated geometry, and this geometry design is the task for generative design algorithm.
Another area and another engineering task is also to develop pipeline for machine learning for some specific task which data scientists often face. This can be AutoML framework, where pipeline is described with a cyclical graph. Due to the fact that pipeline is described by guided cyclical graph, we can have it with different structures. It can be it can have a lot of branches. It can have different nodes inside of different nature. And by doing so, we can solve basically any ML problems, basically on any data. Additionally, to crossover mutation operators, which are the core of the Fedot framework, which has implemented these AutoML algorithms, besides them, we have additional regularization for robustness and flexibility algorithms. They make it possible to improve the algorithms and making them more simple. During the development and design of this framework, we've gathered quite a lot of examples. In parallel, Nikolai Nikitin presents his work, so you can listen to him, but I will skip this section and I will move to the last part. I think it's a very good idea, which demonstrates the creative capacity of engineering mind. It's a specific mathematical task, equation discovery. We need to get the data based on a formulation. For physicists, ML techniques are basically non-used, or people don't really use them. But we obviously can formalize the task to train the model on data as it has been formalized for automatic machine learning, but we will use simple mathematical operations as nodes. And when we create symbolic mathematical models, the only distinction here is that in symbolic mathematical models, oftentimes numerical coefficients with their signs are used. And in order to perform this optimization, we have to use L1 regularization to speed up a convergence and also to improve the structure of the whole model, to make it more stable. By using this example, by using this approach, we can get both isolated mathematical models as equations and systems of equations, like a simplified motion equation system, which is the basis, the foundation of probably all the models for fluid and gas movement. If we generalize it, obviously we can solve problems with derivatives. Without them, we can use just mathematical symbols. As you can see on the right, it's a problem to find this kind of symbolic equation for numerical ranges, for time ranges. And to conclude, all the results are very interesting and are promising. But the most important point here is that all the proposed approaches provide an ability to create an algorithmic engine which can be used to solve different problems by using the whole power of the ML model or other models which exist. And if they do not exist, we can try and nurture this kind of model specifically for our problem. So we can create composites of different models which can solve problems where they were not solved before or were solved poorly. Instead of the conclusion slide, I would like to say these two thoughts. EA are a good basic solution for this kind of creative engineering problems because it's very good to use as a foundation, and that additional procedures and algorithms will have hybrid surrogate solutions. And the nodes, as nodes, we can use different models and different objects or object elements. By doing so, we create composite artificial intelligence systems which open up new possibilities to solve the problems which were not effectively solved with AI, but natural intelligence, human intelligence, they were not really solved in an optimal way. That's all I wanted to say. Thank you for your attention.